We will start our first lecture on the overview of the memory technologies. So this is outline for today's lecture. First, we will use an example that is a smartphone to look at the memory components in such a system. And then we will introduce the concept of the memory hierarchy to talk about different kinds of memories in this hierarchy. And then we will have some examples to show the real memory chips. And then we will also discuss the concept of the array efficiency and also the bit cell size. If you look at the entire VLSI system, so actually there are 3 pillars for building a VLSI system. So you have the blocks for the computation. For example, you have the processor or your logic blocks for the computation. And then the data needs to be stored in the memory, right? So you have different kinds of memories to store the data. And finally, you have to move the data between the computation units and then the memory cells. So you need the communication, interconnect, I/O. So those 3 pillars essentially form the VLSI system. So memory is a very important component into this system. So let's look at a real example. So here, this is a teardown analysis from the TechInsight, which is a company that does the reverse engineering. So it took some, products and then tear down for analysis. So this was done a few years ago for Samsung S20 Ultra phone. And I think this is no big difference compared to today's phone this year. So the major components are still the same, right? So here, if you look at the board after you tear down the smartphone, then here you have many packaged chips assembled on the board. So this is the front side of the board. And you have many big packages. Of course, here then you will have this one. This is actually the processor and co-packaged with the DRAM. So in this case, it's a 12 gigabyte LPDDR5 DRAM. So we will talk about those definitions later, like LPDDR, but basically it's no power, double data rate, 5th generation. So this DRAM is co-packaged with the processor under this package, okay. And then here, this guy is a 256 gigabytes NAND flash for your data storage. So those are 2 biggest package on the board. Of course, you may have many other small packages. For example, you may have here the power management IC to down convert whatever voltage you get from your charger and then manage the voltage delivery to many other chips in this system. So you will have other modules for wireless and those other communication. It's a complicated system. But the biggest component is the processor and then the memory. So here, if you flip the board, you will have more modules assembled on the other side. So many of them are for the power management, the voltage regulation, and so on, and also the Wi-Fi module here. So if you look at the cost breakdown, actually it's interesting. So don't look at the numbers in this chart. but from your, let's say, intuition, what would be the, most costly component in the entire smartphone? Any idea? Processor? What else? Camera. Okay, or you already see this. So yes, so here you can read this later, but here I just want to highlight a few big components. Of course, the processor here is one of the major piece. You have question?
In terms of, so this is material costs, in terms of like design costs, do they stack up relatively the same?
So actually this is the total cost. Yeah, including the material, design, fabrication, tests, and so on. So here you see this is at 2020, right? So the total cost is around $500. But if I recall, this is a flagship high-end Samsung phone, right? So usually it will sell more than 1,000, right? So maybe 1,300 or something. So you can see the margin, I mean, for the profits, right? So here, camera, of course, because it has like 3 cameras, right? So, and then display, it has this the OLED, right? Samsung phone always has that high-end display. And then memory is also a big component, but usually memory is cheap. So that's why it's a tough business. You have to basically memory, if you think about 1 bit data is nanocent, right? $nano, right? So it's very cheap, given this capacity. But here, if you look at the memory, right, it has 2 standalone memory. One is, let's say, volatile, then basically it's DRAM. And then one is non-volatile, basically is NAND flash. So this is DRAM, this is NAND flash. And then there are other memory components, which we didn't talk about separately in this chart. That is because SRAM is integrated with the processor as a cache. So if you just simply look at the silicon space, maybe the processor, let's say half of that is SRAM. Of course, you cannot break down the cost like that way because, SRAM, the design may be, a little bit easier because it's a regular pattern than the logic, right? So the design and the verification, the cost might be a little bit different. But if you look at the silicon footprint, the SRAM actually, more than half of the processor's area spent on the SRAM. Any other questions? All right, so then let's move on. So we're going to introduce a memory hierarchy, which is a very important concept. So here we talk about different technologies. Essentially, they form this memory subsystem in this kind of pyramid hierarchy. So at the very top, you have the processor's core. That is the logic blocks, or your ALU of this processor. And then the processor needs to fetch the data from the caches. And for today's processor, all the caches, I would say 99% of the processor, all the caches are made of SRAM. And then you have different levels of SRAM, like level 1, level 2, level 3. We call L1, L2, L3. So they are on the order of this capacity. So let's say L1 is like 100 kilobytes, L2 like megabytes, L3 like 100 tens of megabytes. So there are differences between those SRAM caches. So that's why we have different levels. The difference is within the trade-off between the latency and then the capacity. So the L1 cache typically run at the same clock speed with your processor. if your processor is like 2 gigahertz or 3 gigahertz, L1 cache, 1 clock cycle. That means the latency is about maybe 0.3. If it's 3 gigahertz, let's say 0.3, less than nanosecond. And then your L2 cache may need a bit longer time, maybe 2 clock cycle. Then you may get like close to 1 nanosecond. And then L3 maybe needs 4 clock cycle, maybe 1.5 nanosecond, something like that. So that is a typical like trade-off in terms of the different levels of the cache. So here I have a simple question. We will talk about that later, but I just want to have a quick test. So SRAM are used for all the caches. They are all SRAMs. Why they show different characteristics, like here, the capacity and then the latency between those 3 levels? So any idea? What's different in those SRAMs? Any idea? Dimensions, yeah. No? Yes or no? Transistor count in total capacity, of course, then depends on the capacity, right? You have more capacity, you have more transistor count. But for each individual bit, it's the same, 6 transistor SRAM. So no, they use similar metal layer. Yes, they of course, then you are closer to the processor core and you have L1 cache, but then it's not really the physical distance. This, of course, the layout, I mean the placement depends on the chip, depends on the the location of the core, but that's not a fundamental difference between those transistors. So fundamentally, the W/L of a transistor is different. So the dimensions, the first answer you have is different. Okay. For L1 cache, because you need fast speed, then you size up the transistor. W/L is larger to provide more current, so you can, charge and discharge faster. So that's why each transistor is bigger. Therefore, given the area, silicon area, you can only have less number of transistors. So that's why the capacity of L1 cache needs to be smaller. If you want to build a large capacity cache, you have to minimize individual transistor size, use a minimal pitch. Then you can get more, but then you need to run slower. So that's a fundamental trade-off in the memory, even within the cache system, right? If you look at the entire memory subsystem, includes the DRAM and then the NAND flash, this trade-off always exists between latency and capacity. The larger the memory is, the slower the memory is. Or in some simple way, you can think like this. The larger the memory is, you have more bits, then take more time for you to locate the data, simply because of the RC wire delay, right? You have a larger memory array, you have so many bits, then it take longer time for you to access the data. So this is the fundamental trade-off, why we have so many levels in the memory hierarchy. Ideally, if there's a universal memory, you want the memory to be as fast as SRAM, and then as large capacity as your NAND flash. But that kind of technology does not exist because it just violates the nature or the physics. So that's why we have this kind of hierarchy. Okay, so here I want to highlight that the caches typically co-integrated with the processor's core. That means this is on-chip memory. On-chip, okay. When we talk about on-chip memory, that means the memories are co-located with your processor's core. And then outside this box, we have those off-chip memory, or sometimes we call standalone memories, standalone. There are two ways. Okay, on chip, sometimes people call embedded memory, the same thing. Okay, then off chip, people call it standalone memory. So for off-chip standalone memory, we have the DRAM, which serves as the main memory of the system, and also we have the NAND flash, serve as your SSD, solid state drive. And then here we have some like new candidates, emerging memories. That's like the emerging memories for the NAS level cache, also a storage class memory. So this is something new that is still yet to be introduced in the product. Some product may have that already, but this is still not the mainstream. Okay, the mainstream is in the black text. Okay. And also here I have a divider here, this red line. So above the line, those memories are volatile, and below the line, the memories are non-volatile. So volatile means, any idea?
It's not permanent, it will the power as well.
Yes. So that's the difference. Volatile means if you turn off the power supply, then the data will be gone. Non-volatile, on the other hand, you will keep the data there. So sometimes people also call this volatile is like a memory, and non-volatile is for storage. So simply longer data retention. And then at the very bottom, we used to have the hard disk drive, and it's not very common these days, especially for your commercial products like your laptop, phone, right? But still in some data center, the hard disk drive is still used for archiving purpose, right? You need to save the large capacity data for a longer time. Then the hard disk drive is still the cheapest way to store the data for longer time. Okay, so any questions on this slide? Okay, so here we show the number of transistor count on a chip for different products over the years. This is a historical trend. And here we collect the data from the CPU, from both like Intel and Apple CPU, and also NVIDIA GPU. So those are the processors, essentially CPU, GPU. And then we have the DRAM, which is a separate die, separate chip, and also the NAND flash is a separate standalone chip. So here, this is the total number of transistors per chip or per die. So you see that this is a Moore's law, right? Exponential increase over the years, over the past 50 or 60 years. And today, you see that the transistor for the processor, this includes the SRAM. So as I said, because SRAM is on chip, so actually more than half of the transistors of the processor is SRAM transistor. But anyway, if you count all the transistors on the processor, including the SRAM, then here is typically like 1 billion to 100 billion these days for the high-end CPU, GPU is on that order. And then the NAND flash actually per die has many more transistors, because NAND flash today, each NAND flash chip can be like terabytes. So that is more than 1 trillion parameters. So the transistor count mostly is for the memory. That's why there is a quote saying that, okay, if you look at all the silicon chips manufactured 1 year globally, 95% of the silicon is used for making memory cells. Simply because NAND flash, DRAM, and also the SRAM on chip occupy most of the silicon space. So any questions here? Oh, the missing data point should be somewhere here. Yeah. I was curious if that is because. So DRAM, no, actually DRAM scales. We will talk about that in more details later. So far, I would say up to today, the scaling trend well maintained. If you ask whether Moore's law is dead or not, I would say no. If you look at the transistor count, okay, per die, it's still on that exponential growth. Of course, there are many challenges in moving forward. Maybe it will, saturate at some point, but still today, it's not. Okay. Any other questions? Okay. So here I have some quotes from this Stanford CS professor. So it says, 21st century workloads is all about big data with a large amount of loosely structured data from all kinds of data, generation mechanisms, because you take video, take pictures all the time that create a lot of data, right? If you think about the entire society, right? Or the camera, on your vehicle or on the surveillance camera, they're generating a lot of data constantly, right? And nowadays, right, you do this ChatGPT stuff, right? So a lot of queries about those natural language problems. So big data simply means big memory. So we need memory to store those data. And of course, after you store the data, you need to process the data, right? So that's why the bandwidth to access the data is also important. First, the capacity. Second, the bandwidth. So here comes this well-known problem in the computer architecture community. There is so-called memory wall problem. So it was first referred to this von Neumann architecture bottleneck. So this was, discussed by this famous book, Hennessy, which was a former president of Stanford, who wrote this famous textbook on computer architecture. And then you see that the CPU and the memory here, this memory really means DRAM. Okay. So the normalized performance gap is increasing over the years. So the performance here is normalized to like the bandwidth. So the processor can, calculate your data very fast because of scaling, because now processor multi-core and so on. So it can process the data very quickly, efficiently. But then the challenge is the I/O, the input and output, the data bus to the DRAM is limited in terms of the bandwidth. So that creates this performance gap. DRAM's I/O bandwidth is limited. We'll talk about why later when we discuss about the DRAM. But this gap is a big problem. So if you look at the recent trend from the GPU workloads, because GPU, very high performance in terms of the flops, floating point operations per second. That is the throughput. So versus memory bandwidth, again, this is the DRAM's bandwidth. This is the data from NVIDIA's, GPU and the latest H100. So here, the latest DRAM, which is HBM2E or HBM3. So there's a big gap in terms of the bandwidth. So this is always a problem for the system's performance or throughput. So that's why the research community is looking into like in-memory computing, right? If you do not move the data back and forth between the processor and DRAM, can we do some processing near the DRAM or in other, even in the NAND flash or other memories without moving the data back and forth? But still, this is a well-known problem right now. From the energy consumption perspective, so here I use some data from this Stanford study as well. So if you look at the breakdown in terms of the energy consumption, this is run on those CPUs in this kind of configuration, like 8-core CPU, and then you have 2 CPUs, and then 128 GB DRAM to run some real workloads for genomics, like the genome sequencing, and also some natural language processing workloads. Majority of the energy spent on the data transfer from the DRAM to the processor. So processor actually consume, a small portion of the energy. Most energy is because you transfer the bits from the DRAM through the data bus to your processor. So that consumes most of the energy. Actually, it's not even DRAM read by the DRAM cell. It's the data that you move from the DRAM through the I/O on the data bus to the processor. So that consumes most of the energy. So that's why memory is becoming the bottleneck of the entire system in terms of the throughput, bandwidth, and energy consumption. So today, large language model, very popular, right? It's all about LLM. So here I got this chart just a few days ago. You look at the model size today. For example, GPT-4 over 1 trillion parameter. So somewhere here. So it will require the memory bandwidth about this like 100 gigabytes per second for like a 1 trillion parameter. But if you look at the available hardware platform, NVIDIA, right, is the major supplier for the GPU. And then the latest product, H100. Okay, it's this one. The B100 is not yet shipped, okay, even though it announced B100, but it's not on sale, right? It's still being manufactured. So what you can buy, the best GPU today is H100, or maybe you buy H200 co-packaged, but that's the best you can get, okay? So H100, if you look at the H100 bandwidth per GPU, only here, even you have 8 of those H100, clustered in the rack, then you get somewhere here. So that's why it's very expensive to run the large language model. You need like dozens of H100, and each H100, the price is over like, I forgot, maybe 200K or something. Like 8 of them is like a few million already, and then you need hundreds of them, then easily like tens of million or 100 million investments in this kind of compute infrastructure. So simply because the bandwidth do not meet the workloads. And we'll talk about the H100's memory configuration at the very end of today's lecture. But basically, the LLM is a memory bounded application. You have to, transfer the model, right, to the DRAM of the GPU, because the model size is so large, like 1 trillion parameter, and then you have to get all those data in at very fast clock speed. This creates this bandwidth problem. So any questions so far?
What is the requirement on time here? Because you have a lower bandwidth, you can still train with an extended period. What is the time limitation?
Okay, yes. So of course, there's trade-off, right? If your bandwidth is limited, then you have to wait longer time. Then that means after you send your query to the GPT, you wait for, you know, like 5 minutes to get your answer, right? You want real-time response in many cases. Yes, so the interconnect is the bottleneck. Yes, because we'll talk about that more in the DRAM lecture. So if there are different kinds of interconnects, and if you, because the DRAM, I didn't bring a real DRAM sample here. It has the pins. Okay, if it's like a DDR kind of DRAM, you have to, you know, plug into the motherboard, and then you have the real data bus. So that's very inefficient because of the RC and then wiring and so on, and also the interface circuits needs to, you know, burn a lot of power to transfer the data at such high speed. So the best way is to do not move the data off chip. Once you move the data from one chip to another chip, it's a headache. So the on-chip interconnect is much shorter, right? It's on-chip, you know, chip is only tens of millimeters square. Then no matter how fast you move, then it's okay. But if you move the data from here to another, to the other location on the board, it's like a tens of centimeter scale. It's not the dominant component. The cell level, like read energy or write energy, is not the major component of the energy consumption. It's the I/O. Okay, so there was a gap between the DRAM and NAND in terms of specs. So this was 2013, like almost 10 years ago. But still, I believe this kind of relative ratio still remains. Yes, the refresh power is about like 10% to 20% of the total power, depending on the technology node. Yes.
Question with the previous chart where you mentioned 8 of H100 or 256. So these we're considering that they're in the same package or
No. This H100 is already a big package. 8 of them means the rack system. Yeah, 8 board.
this is like a real study.
Yeah, this is more like it's not real research where you can, you know, just assume they are, you know, packaged together. This is the real board and the real system. Yeah. So the relative ratio still maintain in terms of the cost per bit. Like DRAM is still like 10 times more expensive than NAND flash per bit. Okay, even though the absolute values, of course, over the 10 years, you know, no longer like 1 gigabyte, you need to pay like $5. Maybe 1 gigabyte right now you only pay less than $1 maybe. But the relative ratio here maintains. And then the speed, not too much difference, even compared 10 years ago. DRAM, you need tens of nanoseconds to read, and flash, NAND flash, 100 microseconds is still on that order. No big change over the 10 years. So here, my point is that the DRAM and the flash very different in terms of the spec. So that creates the opportunity for emerging technologies to plug in between. So if we want to, you know, close the gap Then if you have other technologies that can fit into this gap, then that would be good. But the question is, okay, what kind of technology and for what application? So there are emerging memory research for all over, like, since I started 15 years ago in this business. I mean research, not business. So still the emerging memory, you know, people still call it emerging memory, right? Still emerging. So it's not really like commercialized in mass manufacturing. So there are many challenges. We can talk about them later, but still people have some hope, right? If we can close the gap in this between, let's say, the DRAM and the NAND. So here you see the trade-off in terms of the integration density, number of bits per millimeter square, and also the speed, like DRAM tens of nanoseconds, NAND like hundreds microseconds. So there's big gap here. So that's why not only us, but also the industry try to find some solutions to close the gap. So of course, the mainstream technology like NAND and DRAM keep scaling. Okay, that's why those emerging technologies have not really, occupy a large market space. The reason is that the NAND and DRAM still scale. So that means the integration density keep increasing horizontally, even though the speed, like 3D NAND and 3D DRAM won't help with your speed. It only increase the density, or let's say make the each cell smaller. So you get larger capacity, but it won't help you with the speed. So that's why people are hoping there is a new class of the memory called the storage class memory that could fill in this gap. And there was actually a trial from the industry, 3DX Point of the phase change memory, which was a product actually you could buy from Intel and Micron. It was on sale like from 2015 to maybe 2 or 3 years ago. And then they stopped because they couldn't find the enough customer for that. But if you look at the spec of the 3DX Point of this phase change memory, actually it fits somewhere here. That project failed from Intel and Micron, not because of the technical, okay. Technically they're okay, it's because of the business, okay. So and also the momentum of the the 3D NAND and 3D DRAM, the customers, they're used to the existing technology, and it's more difficult for newer technology to enter the market. And also recently, Micron has like a 32 gigabit FeRAM prototype chip. Still face the same challenge, even though from the spec it looks good technically, okay, but then business-wise, it's difficult to maintain. So endurance, okay, we didn't talk about endurance too much, but endurance means how many cycles, right? You can write or read the cycle, the memory cells. So the NAND has limited, endurance, because here you access them quite less often, right? So then you don't need to read or write many times, right? Because you write or read, maybe every like a second or millisecond, or not millisecond, I mean maybe minutes, right? How often you take the picture, right? So you just need to consider the lifetime, like a 10-year or even 3-year lifetime of your commercial product. Then how many cycles you need to store the data. The endurance for the projector is not good. So what happened? Okay, so maybe let's wait for the projector to warm up. Okay, we only have 15 minutes left. So probably we cannot finish all the lecture today, but that's fine. So what happens? Okay, so let's talk about the array architecture for a generic memory. So no matter it's SRAM, DRAM, or flash, in two-dimensional space, the memory is always organized in this kind of array architecture, where you have the row decoder, colon decoder, and colon marks, and then you have the row address coming and colon address coming. So let's say you have m bits for the row address, n bits for the colon address. Then, you know, after the decoding, you have 2 to the power m rows. And each row is also called VLAN, WL. Each colon is also called bitLAN, BL. And then the intersection of the bitLAN and VLAN will be one memory cell. And here, if you look at total number of cells or number of bits in this array, you have 2 to the m times 2 to the n. And then we have k in front of that. The reason is that here, if we do the decoding, we do not decode every individual bitLAN, but let's say we only decode a group, which is k. It's a k, for example, 8-bit. So every time we decode 1 kilobyte, but I have to emphasize, okay, 1 byte is 8-bit. So if k is 8, then every time you will get 8 bits from the colon. So that means those are 8 colons, let's say 8 colons, k bit as one group. Every time when you decode, you will not decode individual colons within that group. You decode the entire group. That is 8 bits if k is 8. Okay. Of course, you can vary k to be other number, but normally let's say 8 bits. And then after that, you will have the read driver and sense amplifier. Read driver is to write the data in, and sense amplifier is to read the data out. And then you send that to the I/O. So this is a generic architecture. Okay. Any questions? All right, then let's talk about the cell area and the bit area. So normally we talk about the cell area in terms of F square. F is a feature size. That is a theoretical minimal distance given the certain technology node. Okay. So a unit cell will be F times F in two-dimensional space, F times F. And then that is F squared. So, but the memory cell cannot be F squared. The minimal on the two-dimensional space is 4F squared. Why is that? Because you have the row and the colon. So let's say your row, the wire, VLAN wire, you need to pattern that wire from lithography. So you have the F, and then you have the colon, which is another F. But you need to think about the array. Right. So here, even though your memory cell occupies this space, then you have to count this as one unit cell. Because you need the spacing, another F, between the wires, right, as isolation. So each cell will be actually 2F times 2F. That's the minimal you can get. So that's why here I say the minimal is 4F squared on two-dimensional space. Okay. 4F squared. So then here are some typical values for the SRAM. SRAM, we will talk about that later, 6 transistor. But if you look at the layout, depending on the application from L1 to L3, let's say you will get maybe 150 F squared to 300 F squared. So my question is, okay, L3 and L1, which correspond to which? Let's say 150 correspond to L3 or L1. L3, okay. Because L3, you need more capacity. Each cell is smaller, so you use a minimal size. But even minimal size, you will need like 150 F square. So SRAM here, you have 6 transistors, so here. And then DRAM, 6 F square, okay? DRAM is 1 transistor, 1 capacitor. Right now, this is just a schematic. It's not real, this kind of layout. But later we will show the real layout. So it's basically 2F by 3F. Let's say one side is 2F, one side is 3F. So you get 6F square for the DRAM cell. And then NAND, okay. Flash. There's no flash. We'll talk about that later. It's about like 10F square. But we are interested mostly in the NAND flash. So NAND flash is the smallest in terms of the 2-dimensional NAND flash. It's 4F square. This is a theoretical limit, as I said earlier. You just need a 1 word LAN, 1 bit LAN, and then that define one cell. That is 4F square. However, the NAND flash has this multi-level cell capability. That means one cell, you can store multiple bits. So here, that means if you have multi-level cell, because SRAM, DRAM, those are just the binary memory. You can only, one cell can only store like 1 or 0. It's 1 bit data, 1 or 0. But the flash, you can store multi-bit data. That means you can store 0, 1, let's say 0, 0, 0, 1, 1, 0, 1, 1 into one cell. So this equivalently will be 2 bits. If it's 2 bits per cell, then each bit will be 4F squared divided by 2, right? Or you can do more, like 3 bits per cell, then it will be 4F squared divided by 3. So even though here you have the like one transistor, a flash transistor, 2F by 2F, depending on how many bits you store, then equivalently you will be like a 4F squared divided by n, if n is, n bits. But today's NAND flash already has transitioned to the 3D NAND flash. So instead of, laying down the transistor, it's a NAND string, right? NAND in configuration, NMOS transistor will be in a string. So 2D NAND is like you have those transistors, on the plane, on the silicon substrate. But 3D NAND flash, tilt this by 90 degrees, you are building the transistors vertically out of the plane. This is how you save the space, right? Still on the 2D space, on the substrate of the silicon, you only have 2F times 2F. But now you are building the transistors vertically. Then you have the number of L. This is L layers, right? Then equivalently, 1 bit will be 4F squared divided by n. N is n bit. You can still do n bit in the 3D NAND flash. Now you need to divide by L for each bit equivalently on the 2-dimensional space. If you project that 3D NAND flash, to the 2D footprint, each is very small. And nowadays, L more than 300 layers from the latest product from the industry. So that's why flash is so cheap, right? Because each bit consumes so little silicon space. So any questions here? Okay, so this slide is important. You may have questions in your homework or even exam on this, okay? I won't repeat.
Since for the 3D NAND flash you're stacking 3 dimension, how does the yield compare to a traditional 2D NAND?
Oh, so the yield depends on how the company, optimize. But to make it qualified as a product, the yield should be 99 point something, right? To make it a product. Yeah, so it's no big problem. I mean, the industry already solved the problem. Yeah. All right, so here another concept, array efficiency. So if you look at the, let's say this, I think this is a 2D NAND chip. So here you have the NAND plane, and then you will have some peripheral circuits. Row decoder, for example, here this part is the row decoder, and then at the end of the column you have the column like a peripheral circuit, sense amp, and so on, and then some high voltage charge pump circuits. So basically, for the memory chip to be functional, you need many of those peripheral circuits. So here we are interested in the area occupied by the memory cell, which is this part and this part. So the array efficiency is defined as the area percentage occupied by the memory cell over the entire chip, okay, entire memory chip. So for here, this NAND flash, you see it's like 70 to 80% of the area should be spent on the memory cell instead of your peripheral supporting circuitry. So this is to reduce the cost, because you still want most of your silicon space spent on the memory cell where you store the data. Then those peripheral circuits is to assist you to write the data in or get the data out. Ideally, you don't want them at all, if possible, right? But then, of course, you need some assistance from the circuits. So here, you want to maximize the array efficiency. If it's a good design for the memory, that means you want to improve array efficiency. Because the peripheral circuits here typically include the decoder, sense amp, control logic, and then charge pump for high voltage generation on chip. So this is for the DRAM, the same for the, and this is for NAND, the same for the DRAM. But I have to emphasize a little bit different from the processor, because processor, if you look at the processor, this is like a processor's die image. So it has many logic blocks, cores, right? You have the CPU cores. So here, we look at the L3 cache, this region. So it's a shared L3 cache by those 8 cores. So here the L3 cache is SRAM. Even within the SRAM, you see different colors here. So maybe here this part is the memory, and then this part is the peripheral circuits. So here, when we talk about the array efficiency of the L3 cache, we talk about the memory cell here divided by the L3 cache area. We are not talking about the memory cell here divided by the entire processor. Because entire processor here, you have other cores. So here, when we talk about the processors, 30% to 50%, we need to specify which cache level, And then we look at within that cache level, how many percentage of the silicon occupied by the SRAM cell. But typically, the processors, array efficiency, I mean the cache array efficiency is lower. All right, so I think we don't have time to finish the lecture, so we may have to speed up next time. We will stop it here for today, and we will meet on Thursday. Thank you.